Titrations are a form of volumetric analysis where the number of moles of one solution is calculated by adding a volume of another solution of known concentration. This just produces a complete reaction. Only one reaction can occur between the solutes contained in the two solutions, and the reaction must go rapidly to completion.
We also need to be able to signal the equivalence point.
For an acid-base titration, the equivalence point occurs when the number of moles of hydronium from the acid is equal to the number of moles of hydroxide from the base. This is not necessarily when the moles of acid equals the moles of base. For example, the acid could be diprotic, but the base could be monoprotic. At least one of the two reacting species must be strong to ensure that the reaction goes to completion. Before the titration, a small amount of indicator is added to the reaction vessel. The indicator used must change color at or very near the pH associated with the equivalence point. Titrations require precise instruments and careful measurements to ensure the accuracy of the data collected. This is the apparatus used for a typical titration. A pipette is used to draw up a precise volume of the solution being analyzed. Here it is acetic acid, which is then transferred into an Erlenmeyer flask. A small amount of an appropriate indicator is added to the flask, in this case phenolphthalein. The flask sits under the burette, which contains the standardized solution. In this example, it contains sodium hydroxide. The solution in the burette is called the titrant, and the solution in the flask is called the analyte. We carefully add the titrant to the flask until the first permanent color change of the indicator occurs. This is called the transition point or end point of the indicator, and it signals when the equivalence point has been reached. As we approach this point, we want to add the standardized solution more slowly so we don't overshoot. Once we reach the end point, we close the valve on the burette and determine the volume of the standard solution we used. The measurements we get off the burette are recorded to 2 decimal places. The pH of the transition point only depends on the chemical nature of the indicator and is independent of the equivalence point. Likewise, the pH at the equivalence point is only dependent on the chemical nature of the reacting species and not the transition point. As an accuracy check, titrations should always be repeated. Those experienced with titrations should have values that agree with each other within 0.02 milliliters, but it is fine for students performing titrations for the first time to get values within 0.1 milliliters. If the volumes do not agree within the decided uncertainty, then more trials must be completed until they do so. The volumes must be averaged once agreement between data in 2 trials occurs.
For a titration to be successful, we need the concentration of our standard solution to be accurately known. There are 2 ways we can go about this. One is using a primary standard, which is stable and available in highly pure forms. These include potassium hydrogen phthalate, oxalic acid dihydrate, and anhydrous sodium carbonate. We can also standardize a solution we want to use if it is not available in a highly pure form. We must titrate it with a primary standard. The standardized solution concentration is now known. Here's an equation we would use if we were standardizing sodium hydroxide using oxalic acid dihydrate.
Four kinds of common titration calculations are ones where we determine solution concentration, solution volume, molar mass, and percent purity. We will go through an example of each. Before that though, here are some quick tips. It is a great idea to begin by writing the balanced chemical equation as we will need this for our calculations. We must also pay very close attention to significant figures, which we should already be doing all the time. The calculations basically consist of 3 steps, but step 1 and 2 can be combined. The first step is using the data to determine the moles of the species used. Then we use the moles from step 1 and the mole ratio to determine the moles of the other reactant consumed. Finally, we use the moles from step 2 to determine either solution concentration, solution volume, molar mass, or percent purity. Okay, now let's try a solution concentration problem. As you might have noticed, this example comes from the 3D animation we showed earlier. A student has titrated 25 ml of acetic acid solution with 0.125 molar sodium hydroxide. The results are recorded in this data table. By subtracting the initial volume from the final volume, we get a volume of the sodium hydroxide actually consumed. The closest values are in trial 2 and 3. Trial 1 is more than 0.1 milliliter different, so we can reject it. The volume we will use in our calculations is the average of trial 2 and 3. We convert the volume of sodium hydroxide to moles of acetic acid using the molarity given by the question and the mole ratio from the chemical equation. All we need to do now is divide the moles of acetic acid by the initial volume to give us the solution concentration. Like other titration calculations, we begin the solution volume question by writing the balanced chemical equation. A standardized solution of hydrochloric acid has a pH of 0.537. How much do we need to add to 25 mL of 0.225 molar strontium hydroxide to reach the equivalence point? Well, we can get the concentration of hydronium and therefore hydrochloric acid from the pH. We then convert the volume of strontium hydroxide to moles of HCl. Multiplying the moles of HCl by the inverse of the concentration we calculated in the first step provides our final answer. A 2.552 gram sample of a monoprotic base is diluted to 250 milliliters. A 25 ml sample is then titrated to the equivalence point using 17.49 ml of 0.05115 molar hydrochloric acid. What is the molar mass of this base? Well, once again we write the balanced chemical equation first, and then convert milliliters of HCl to moles of the unknown base. Now we want to find the moles of the base in the original sample. There are probably several ways to do this, but I just multiplied the original volume by the concentration of the sample we titrated. This works because the concentration should be the same in both of them. Dividing the mass of the base in the original sample by the moles in the original sample gives us the molar mass in grams per mole. The final example we will do is a percent purity calculation. 1.275 grams of impure nicotinic acid is dissolved in water to form 20 ml of solution. 18.36 ml of 0.5 molar potassium hydroxide is needed to reach the equivalence point. We need to find the percentage purity of the sample. After writing the balanced chemical equation, we are able to convert milliliters of potassium hydroxide to moles of nicotinic acid. This is the moles of pure nicotinic acid, since it is what reacted with the base. Multiplying this by the molar mass gives us it in grams. Now we can find the percentage purity, which turns out to be 88.6%. And remember that the percentage purity is the pure mass over the impure mass multiplied by 100%. We usually use either an acid-base indicator or pH meter to measure the pH of a solution. An acid-base indicator is a weak organic acid that is usually monoprotic and whose conjugate pair displays different intense colors. Here is a typical equilibrium for an indicator. The acidic form has an extra proton and is on the left, while the basic form is on the right. As the concentration of hydronium goes up, the equilibrium will shift to the left and more of the acidic form will exist in the solution. This means that the color of the acidic form will predominate. If the hydronium concentration was to go down, like if we added a base, then the equilibrium would shift right, making more of the basic form of the indicator. Then the basic form's color would predominate. Indicators differ from a buffer for two reasons: their colors and the smaller quantities used. The changes in indicator colors occur over a range of pH values. Generally, 1/10 of the indicator must be converted to its conjugate for us to notice a change in color. Halfway through the color change is the transition point or endpoint of the indicator, where we see an intermediate color. At the transition point, there are equal quantities of the acid and base form of the indicator, so the Ka equals the hydronium concentration. This tells us that at the transition point, the pKa of the indicator equals the pH. The useful pH range for an indicator is generally the pKa plus or minus 1, which has to do with the fact that this is the range where we would witness the color change. Averaging the two pH values associated with the range over which the color change occurs can give us the indicator's transition point pH and pKa value. Several different indicators can be combined to create something known as a universal indicator. In a universal indicator, the colors of the component indicators at each pH combine to display virtually all colors of the visible spectrum. This table shows the indicators that make up a typical universal indicator. we can see how their individual colors combine to give an overall color revealing the pH of the solution.
Let's do an example of a calculation involving indicators. The indicator bromethymol blue appears yellow at a pH of less than 6.0 and blue at a pH greater than 7.6. We need to find its Ka and pKa values and the color it would turn when added to a solution of 0.00010 molar sodium hydroxide. First, we can average the two values associated with the color change range to give us the pKa of the indicator. 10 to the negative power of this value will give us our number for Ka. The solution of sodium hydroxide would have a hydroxide concentration of 0.00010 molar. After converting this to the pOH, we can subtract it from 14 to get the pH. Since the pH is above 7.6, the indicator must turn blue.
A titration curve is the plot of the pH of the solution being analyzed versus the volume of titrant added. We are going to analyze three different types of titrations and the titration curves that go with them. The first one we will look at is for a strong acid and strong base titration. Here we are titrating 25.00 milliliters of 0.100 molar hydrochloric acid with 0.100 molar sodium hydroxide. The pH starts out low because there is excess strong acid in the flask. The pH slowly increases until the moles of sodium hydroxide almost equal the moles of hydronium in the flask. The curve then increases dramatically and becomes almost vertical when we are only a few drops away from the equivalence point. After this, the pH rises slowly as we add excess hydroxide to the flask. There are four key stages we will calculate the pH for. The first is prior to adding the titrant and is pretty straightforward. We only have HCl in the flask and it is a strong acid, so we can just take the negative log of its concentration to find the pH. The next stage will require a bit more work. We are halfway to the equivalence point, so we've added 12.5 milliliters of sodium hydroxide. This means we need to calculate the concentrations of hydrochloric acid and sodium hydroxide because they have both been diluted. After that, we create an ICF table or Newt box to get the final concentrations. The concentrations we just got can go into the initial row. The reaction goes to completion and sodium hydroxide is the limiting reactant, so we subtract 0.0333 from the left side and add it onto the right side. The final hydrochloric acid concentration is equal to the final hydronium concentration. Using this, we can calculate the pH.
At the equivalence point, we must consider the dilution of the hydrochloric acid and sodium hydroxide. 25 milliliters of the sodium hydroxide have been added at this point, which will completely neutralize the hydrochloric acid. It appears as though the concentration of hydronium and hydroxide are zero, but this cannot be the case. The product of the hydronium concentration and the hydroxide concentration must equal 10 to the power of negative 14. Neither is in excess, so both must be 1 times 10 to the negative 7. This gives us a pH of 7. It makes sense that the titration of a strong acid by a strong base produces a solution with a neutral pH, because neither of the ions present in the product salt can undergo hydrolysis to affect the pH. A question like this could also ask what indicator would be suitable to use. The large jump in pH that occurs with a single drop of titrant at the equivalence point means we have more flexibility in our options. If we looked at our chart, we would see that indicators with transition points as low as pH 5 and as high as pH 9 would work for this titration. For example, we could use something like methyl red, which undergoes a change from pH 4.8 to 6.0, or phenolphthalein, which undergoes a change from pH 8.2 to 10.0.
What is the pH after we continue to add base after the equivalence point? If we added 30 mL total of sodium hydroxide, then we still account for the dilution and make an ICF table. This time the hydrochloric acid is limiting and we are left with excess sodium hydroxide. Using the hydroxide concentration, we can get a pOH, but we need to convert this to a pH value. All answers we calculate should have the correct sig figs. In this case, our concentrations were good to 3 sig figs, but subtracting them in the ICF table left us with 2 sig figs. When we are dealing with the logs, the amount of sig figs of the number we are taking the logarithm of determines the number of decimal places in the final answer. Now we will go through an example of a weak acid being titrated with a strong base. In this case, 25 mL of 0.100 molar acetic acid is being titrated with 0.100 molar sodium hydroxide. The acid is weak and only ionizes to a slight extent, so the initial pH is higher than it was with the strong acid. After an initial jump, the curve increases more slowly over a curve known as the buffer region. The curve in this region still increases more than the strong acid. At the equivalence point, the solution contains the anion, acetate, from the weak acid, and the cation, sodium, from the strong base. The cation won't react with water, but the anion is a weak base and will accept protons from water. This results in a pH at the equivalence point that is greater than 7. Beyond the equivalence point, the pH rises slowly as excess hydroxide is added. Once again, we will calculate the pH at the same 4 key stages, as well as some additional ones. However, calculating the initial pH is a little more complicated this time. Because we are dealing with a weak acid, we need to create an icebox where X is the concentration of hydronium. The minimal ionization, which is less than 5%, of the acetic acid allows us to assume its initial and equilibrium concentrations are the same. We plug these values into our Ka expression and solve for the concentrations of X. We then take the negative logarithm of this concentration to get the pH. To find the pH just before halfway to the equivalence point, let's say we added 12 mL of sodium hydroxide. Just like with the strong acid strong base example, we account for the dilution of the concentrations. We create an ICF table and see that the sodium hydroxide is limiting. There is now enough of the acetic acid and acetate ion in the solution that a buffer system exists. We could use the Ka expression to find the hydronium concentration and then convert that to the pH, but another way of solving this is to use the Henderson-Hasselbalch equation, since it is a buffer we are dealing with. This gives us a pH of 4.71. At halfway to the equivalence point, the concentration of the acetic acid and its conjugate base are the same. This gives us a logarithm of 1 in the equation, which is equal to 0. The pH is equal to the pKa of the weak acid at halfway to the equivalence point. Just after halfway to the equivalence point, we can say we've used 13 mL of sodium hydroxide. After calculating the initial concentrations after they've been diluted, we place them in an ICF table. Once again, we can use the buffer equation because there are appreciable quantities of acetic acid and its conjugate base. Once we've reached the equivalence point, we have used 25 milliliters of sodium hydroxide. Our ICF table reveals that a 0.0500 molar solution of sodium acetate now exists in the solution. The anion of this dissociated salt is the conjugate base of a weak acid, so it can accept protons from water. We use the hydrolysis reaction and an ice table to help us calculate the pH of the solution. 0.0500 molar is entered into the initial row for the acetate, and the change from X is negligible. We need to calculate the Kb value of the acetate, which we can do by dividing 10 to the power of negative 14 by the Ka of the conjugate acid. Then we put our concentrations from the ice table into the Kb expression and solve for the concentration of hydroxide, which is X. We can then convert this to the pH by subtracting the pOH from 14. Calculating the pH beyond the equivalence point is almost identical to what we did with the strong acid strong base reaction. Although there is some acetate in the solution, we ignore this since there is excess sodium hydroxide. We simply use the concentration of hydroxide to give us a pOH value and subtract that from 14. This pH is the same as the final one from the strong acid strong base titration, but the pH at the other 3 stages was different. Let's briefly take a look at our titration curve to see where we would place our pH values. Before we add any strong base to this solution, it is acidic. The pH is 2.87. Just before halfway to the equivalence point, we can use the buffer equation to come up with a pH of 4.71. Halfway to the equivalence point, the pH is equal to the pKa of the weak acid. This is 4.74. Slightly after halfway to the equivalence point, we get a pH of 4.78. Once we reach the equivalence point, we have the conjugate base of the weak acid in the flask. This gives us a pH of 8.72 after we create our hydrolysis table. The best indicator to use is the one that's pKa is closest to the equivalence point. In this case, it is thymol blue, which has a pKa of 8.8.
After we pass the equivalence point, we are left with excess space in the flask. This will solely determine the pH. In this case, we got 11.96.
Now let's compare the two different titration curves we've worked with. As the strength of the acid being titrated decreases, the portion of the titration curve before the equivalence point will shift farther and farther up. However, both the weak and strong acid require the same volume of base to be neutralized.
The final example we will look at is a weak base titrated with a strong acid. The graphs when we are titrating a base look similar to the acid ones we were just looking at, but are inverted. For a weak base, we expect the initial pH to be above 7 but lower than that of a strong base. There is an initial drop in pH for the weak base, but over the buffer region the pH decreases more slowly. However, it is still changing faster than the strong base curve. The steep drop at the equivalence point occurs over a smaller range for a weak base than a strong one, and for a weak base the pH at equivalence is smaller. Both require the same volume of acid to be neutralized. Before we have added any acid, we would start with a Kb ice calculation. Throughout the buffer region, we would use the buffer equation. Halfway to the equivalence point, the pH would be equal to the pKa of the conjugate acid. At the equivalence point, we would do an ice calculation for the conjugate acid. As we continue on through the titration, we would calculate the pH using the excess hydronium. These calculations are very similar to the ones we have just done. Since we have already gone through the calculations for a strong acid strong base titration and a weak acid strong base titration, we will go through these calculations a lot quicker. The only difference is that we are dealing with a base being titrated with a strong acid. All the work will still be displayed on the screen, so feel free to pause the video if you need to.
To calculate the initial pH, we need to remember that we are dealing with a weak base and need to use the Kb value. We might need to use our Ka to find the Kb value if it is not given to us by the question. We also make an icebox and put the values into the Kb expression. Not surprisingly, the pH we get is quite basic, as we haven't added any acid to our base yet. Getting the pH just before halfway to the equivalence point is basically like what we did for the weak acid. Keep in mind, if we were to solve for the pH after adding some other given volume of strong acid that wasn't one of the 4 key points we've talked about, we would likely use an ICF box as well. For instance, if it was 10 milliliters or 50 milliliters of acid that was added, we would use an ICF box. At halfway to the equivalence point, the concentrations of ammonia and its conjugate acid are equal, so we can use the Kb expression to solve for the hydroxide concentration. Then we can convert that to the hydronium concentration and pH. We also could have used the buffer equation here like we did for the weak acid strong base question. Now you can see both ways of solving the pH at halfway to the equivalence point. When we add 25 milliliters of hydrochloric acid, we have reached the equivalence point and all the ammonia has been neutralized. The ammonium remaining in the flask, its conjugate acid, will donate protons to the water, so we can use an icebox and Ka expression to get the equilibrium concentration of hydronium. Finally, when we have added 30 milliliters of hydrochloric acid, then there is excess hydrochloric acid in the flask. The ammonium can be ignored and the concentration of hydrochloric acid will solely determine the pH. Metal oxides and nonmetal oxides. Metal oxides are formed when group 1 alkali metals and group 2 alkaline earth metals react with water to produce a basic solution. They are also referred to as basic anhydrides. For metal oxides to react with water and produce a basic solution, they must be both highly ionic and soluble. For example, we can look at sodium oxide. Sodium oxide reacts with water to produce sodium ions and hydroxide ions. Nonmetal oxides that react with water are known as acidic anhydrides. In such a reaction, because no oxide ions are released into the water, no hydroxide ions are produced. The water molecule binds to the molecular oxide, forming a molecular acid. Acidic anhydrides are normally those containing nonmetals with relatively high oxidation states. For example, sulfur trioxide reacts with water to form sulfuric acid. Acid rain is when the pH of rainwater is below 5.6. This is caused by humans burning fossil fuels. A nonmetal oxide in our atmosphere reacts with water to form an acid.
Both nitrogen oxides and sulfur oxides contribute to acid rain. The problem increases in polluted air that contains ozone and fine dust particles. The presence of sunlight, oxygen, and ozone oxidizes some of the sulfur dioxide to sulfur trioxide, which will form the strong acid sulfuric acid. Fortunately, there are some reasons for optimism. Some lakes containing dissolved limestone are able to resist changes in pH from acid rain. Modern vehicles are equipped with a catalytic converter, which greatly reduces levels of carbon monoxide, unburned hydrocarbons, and nitrogen oxides released into the atmosphere. The scrubbing process removes sulfur dioxide from industrial exhaust streams by using calcium carbonate. Other processes involve using hydrogen sulfide to convert sulfur dioxide into elemental sulfur, and using gaseous ammonia to reduce nitrogen oxide emissions. This chart is an excellent summary of all the calculations we have been doing throughout this chapter. When we are confronted with one of these problems, we must first decide if we are dealing with one substance or a mixture of two substances. If it is only one substance, we need to determine if it is strong or weak. Strong acids and bases completely ionize or dissociate, while weak acids and bases would require a Ka or Kb ice table. For bi-ions, we compare the Ka to the Kb. If we are given a mixture of two substances, we need to determine the initial concentrations with a dilution factor. If it is a buffer, we can use the Henderson-Hasselbalch equation. If it is an acid and a base, we need to neutralize them, and know whether it is a strong and a strong or a weak and a strong. For a strong and a strong, we would make an ICF box to determine the concentration values at this point. If it is a weak and a strong, there are three different scenarios. We could have excess strong, we could have excess weak, which means we can use the buffer equation, or we could have equivalent quantities of acid and base. If we have equivalent quantities of acid and base, then we need to know what the salt does in water, and we may have to use a Ka or Kb icebox to find the concentration of hydronium or hydroxide.